Hey, hello everyone. Welcome to our channel Physics, where we actually learn physics. Okay, so we have already seen what are random errors and what are the systematic errors. Okay, we have already discussed a lot about systematic and the random errors and what are the different causes for the random and the systematic errors. Okay, so over there, okay, in those two lectures where we discussed the systematic as well as the random errors, okay, so we saw there that systematic errors are something that we can control in some ways. Okay, if you take proper precautions, if we do the experiments properly, okay, if we somehow remove our personal bias or something like that, so these errors, the systematic ones, can be controlled in some ways. Okay, at least we can identify them, we can control them, we can minimize them. But in the case of random errors, we saw that it is quite difficult to first of all identify the causes of random errors, because generally the causes of random errors are different at different times. Okay, and the causes keep changing sometimes. In some experiments, the causes of random errors keep changing. In fact, it becomes really difficult to identify what are the main causes of these random errors. Okay, so the problem is how to identify them, and if we are not able to identify, how would we minimize them? It's really difficult to minimize them, it's really difficult to control them. Okay, so it becomes a problem as a scientist, as a researcher, or as a experimentalist whenever we are dealing with such kinds of errors. And the problem is, even if the systematic errors are present or not, random errors are always present in any experiment, in any measurement. Whatever we do, random errors are most likely to pop up somehow. We just can't know that. It's really difficult to predict whether there is any error or not just because of these random errors. It becomes really difficult as a scientist, as a researcher, whether the measured value has any error or not. Finding out that is quite difficult, because maybe we have removed this systematic error somehow by taking the precautions, but random errors are such for which we don't know the actual reason. They may pop up by any reasons. Okay, just like we talked in our previous lecture, random errors may arise due to any small fluctuations in the surroundings, maybe. Okay, maybe in some external conditions may just change, maybe some internal conditions just change a little. So all these small fluctuations may just bring this random error, okay, in our measurements. So what to do now? What to do with our measurements? How to identify whether there is any error or not, and how to identify whether our measured value is actually the true value or not? That is our main job, isn't it? We want to find out the true value for any physical quantity that we are measuring. Okay, we want to find out what the true value of the physical quantity, okay, which we are measuring. For example, we are measuring mass, just example, we are measuring length, okay, we are measuring the time period, okay, something like that, or maybe current, voltage, okay, density, anything, volume, whatever you say. But for those physical quantities, we want a true value somehow. Okay, but because these random errors keep coming, okay, keep coming in, we can't really identify whether our measured value is a true value or not. How can we identify, and how can we surely say that yes, this is the true value? Can we say that yes, it is the true value? Can we say that it does not have any error in it? Isn't it? There is no way to tell. Okay, why I will tell you why there is no way. Because when we carry the same experiment 2 or 3 times, we always find that the value for the measured quantity varies a little. It varies a little, always. For example, you are finding out the time period of oscillation. Time period of oscillation of a simple pendulum, for example. So in that case, we find out that when we do the experiment, let's say 2 or 3 times, every time we get a value that is little bit less or more. For example, in the first case, we got a value like 1.31. The next time we get 1.33. Maybe next time we get 1.29. So you can see what is happening. And it's not that I am telling these values, these are the actual values that generally people encounter with. These are the actual differences in the values that we encounter. Okay, if you have never done any experiment, just go and do any experiment with such kinds of things. You will always find out there are small differences. Okay, so these are only because of the random errors. So now the big question arises, how to remove them? How to minimize these random errors? That's the main question, isn't it? How do we do it? And in fact, how do people in science, in research, remove it or identify it or control it? How do they do it? Okay, so it's a big issue, isn't it? It's a big issue because we want accuracy. We want to be as close as to the true value of the physical quantity, isn't it? We want to be as close as possible. So how to remove this? Okay, see, because of this random errors, there is always this uncertainty in our mind. Okay, there is always this uncertainty. Yes, there is something wrong. There is something wrong with my readings, with my experimental data. Something may be wrong because of the random errors. So you can see here, there is always this uncertainty, and we call this uncertainty as the error. And right now it's a random error. So identifying these random errors and identifying the causes, okay, and minimizing them, that's the main issue over here. So how to do it, isn't it? That's the big question. Okay, so for this there is an answer. Okay, in fact, it's quite difficult to minimize them. Okay, it's quite difficult to minimize them, but at least it is, it is easy, or there is some way to at least identify these random errors. Okay, at least find out what is the approximate value. What is the approximate value of these errors? At least we can find out. Okay, so there is a theory called as error analysis. There is a theory called as error analysis. Okay, using this theory, we can actually analyze the data. Okay, and not only this, after analyzing, we can actually find out what are the approximate values of the errors. Okay, and that's the main issue, and that's the main thing that we are looking for. Okay, so that's what we do in this theory. Error analysis is something definitely related to errors. How to find out the errors, how to approximate those errors, okay, how to represent values, okay, and find out the errors in the results, okay, etc. There are lots of things actually which we are gonna discuss. So now we are gonna see a way to identify the true value. Okay, we are gonna see the way to identify the true value of the physical quantity under measurement in case the random errors are irritating us. Okay, and they are definitely irritating us. Okay, they are always there. Okay, we can't really say irritating, but yeah, they are there, always there. Okay, it's we can say it's like they are inherent to any measurement that we do. Okay, random errors are inherent. It's a very important word, inherent. Okay, they are always there. Okay, because we are really unaware of the causes, okay, and the causes keep changing. So it's a big issue actually. Anyways, so now we are gonna move and we are gonna see how exactly we identify them and how exactly we come across the true value of the physical quantity under measurement. Okay, so let's see what do we do over here. So the first step is this one. Okay, first step is to find out the best possible value. Okay, best possible value. Okay, now over here at the top I have written some names. Okay, I have not yet talked about them, but believe me, we are gonna go there. That is the main topic for today's lecture, but these are also very important. Okay, so now the first step is to find out the best possible value. Okay, now what is the best possible value? Okay, see, now suppose for a simple example, okay, let's say you are doing an experiment with a simple pendulum. Let's say this is a simple pendulum, okay, and you are finding out the time period of oscillation. Okay, let's say you are finding out the time period of oscillation t. Okay, what is this t? And you really want to find out the true value. Okay, now let's say while doing the measurement you got some value. Let's say your first reading says that t is equal to, let's say, 2.32. Just an example. For example, time period is equal to 2.32 seconds. Just an example. This is first reading. Now when you do the second reading, when you get the second reading says that it's 2.34. Okay, and it happens, believe me. Okay, then next reading says it's 2.31. Next says that it's 2.30. Next one says no, it's not, it's 2.33. So you can see, and if I go and do multiple measurements, I will find maybe some same readings, maybe a little bit different readings, who knows, and the causes may be anything. And because of this scatter, okay, you can say it's a scatter of values. So because of this scatter, there is always this uncertainty in our minds, isn't it? There's always this uncertainty in the mind. Which value is the true value? Which is the true value? No idea at all. Okay, no idea. I mean, see, for example, if I say yes, this is the true value, for example, okay, if I say that it is the true value, when I say that this is a true value, that means I am saying here that this has no error. This has got no errors. But are we really sure about that? That it is not having any error? We can't really say. Okay. Because our other readings say that no, the true value is different. The time period is also having other values. That means maybe this has an error. Maybe. Okay. Maybe it may be a true value. Maybe. Who knows? Okay. We can't really say. It may be a true value. Who knows? But are we 100% sure? Is it the true value? Okay, so directly we can't say that it's a true value. It would be like overestimating this value as a true value. We can't overestimate any value as a true value because there are other values also. Okay, so these values can also be the true value. Okay, so suppose I say this is the true value, then what about these values? Are they not the true value? But are you aware that any one of these is a true value? No, it's all a mess actually. It's all uncertain. Okay, right now it's all uncertain. Okay, so for example, out of these values, there may be one true value. For example, this one, maybe. So if you assume this one as a true value, you are overestimating this as a true value, but at the same time, you are underestimating this as a true value. Okay, so you can't even overestimate anyone You can't underestimate any value. Every value that you get is important. Okay, every value, every measured value that you get is important over here. You can't underestimate any value. You can't overestimate any value. Okay, underestimating means ignoring it. We can't ignore that, because this is the value that we have got from our experiments ourselves with our experiments. Okay, the variations that we are getting, that is only because of the random errors that are popping up. That is not our fault. Actually, we have taken all the precautions. So that's why we can't underestimate, we cannot overestimate also any value as being the true value. Okay, so what to do now? What to do now? Okay, so the best way for this is to take as many readings as possible. Okay, the best way is to find out as many readings as possible. Okay, do the measurement thousands of times. Okay, just example, thousands of times, but take it as many times as possible. Okay, numerous times. Okay, take it numerous times. And then in that case, the value that you get, okay, values that you get, okay, will be, kind of a groups actually. You, for example, this value, when you take 1000 times, okay, when you take the readings 1000 times, you will get this value. Okay, like 50 times, 60 times, you will get this value. 100 times maybe this value, 200 times maybe. Okay, but at least we will get one estimation, okay, about the true value. Okay, now we will see what exactly we do over here. Okay, so as I said, the first step is to take as many readings as possible. Okay, as many readings as possible, numerous. Okay, generally that is what we do. For example, when people in nuclear physics, for example, okay, or particle physics, they do the experiments, they do it for years. Okay, it's not for just 1 or 2 days. People in astrophysics, they do the experiments for years. Okay, they take readings for years. It's not just for 1, 2 or 1 month. Okay, no, they do it for years. Okay, for example, you are finding out how many cosmic rays are entering the earth. Okay, how many cosmic rays are entering the earth in, let's say, per unit area, let's say, or per day, for example. Okay, so you can't just take the readings for 1 day or 2 days. You have to take readings over the whole year or maybe more than that. Okay, and then after taking all those readings for many days, then we can take an average of these values, and that value will tell us about the approximate number of cosmic rays that are entering our surface. Okay, so that is one of the ways. Same thing with all the experiments that we do, same thing with all the measurements that we make. Okay, what we do is we take thousands of readings, multiple readings, and then we take the average of all these numbers. Okay, average of all these numbers, and this average, or we can say the arithmetic mean. Okay, the arithmetic mean or the average of all the measurements is considered as the best possible value. Okay, it is considered as the best possible value. Okay, so it's very simple. The definition of this best possible value is what? The arithmetic mean or the average of all the measurements is considered as the best possible value. Okay, so it's very, very, very simple. Okay, so suppose for example, in an experiment we have got some measurements for some physical quantity. Let's say these measurements are A1, A2, A3. Okay, and let's say there are n number of such quantities, I mean such values. Okay, so we have done the measurement n times, n number of times. Okay, and we have got these values. Now what we do is, see, out of all these n values, some values may be equal, some may be same, but most of them would be different also. Okay, so what we do is, we can't underestimate anyone, we can't overestimate anyone. What we have to do is, we have to take an average or the arithmetic mean, and this arithmetic mean is called as or considered as the best possible value. Okay, and this best possible value is itself treated as the true value of the physical quantity under measurement. Okay, this best possible value is considered as what? The true value of the physical quantity under measurement. Okay, so that is what we do. Okay, so it's really easy to find out the average or mean. How do we do it? It's very simple. A mean, let's call this as A mean. Okay, A mean is what? The mean of all these numbers. Okay, so it's very simple. How do we do it? Just add all the numbers. Okay, so A1 plus A2 plus A3 plus there are n number of such quantities. Okay, I mean values. Okay, so there are n number of such values. We have added all of them, and now we will divide by the number of measurements. Okay, or number of values. The summation of all the readings divided by number of readings. Okay, summation of all the readings divided by number of readings. That gives us the arithmetic mean of any measurement, any number of measurements. Okay, and that is how we find out the best possible value. Okay, so this best possible value is considered as the true value of the physical quantity under measurement. Okay, so this is a very important term over here, best possible value. Okay, just fit it in your mind. Okay, that it's the very important term. Okay, because everything depends on this, because in most cases, we don't know what is the true value, because we see the scatter. Okay, there is a scatter of values, which value to take as a true value. So we have no idea. So that's the idea. Take this average, that is our best possible value. And mostly it is seen that when you take thousands of readings, okay, most of the values are close to one value. It is always seen that most of the values are close to, or we can say they are converging towards one value. Okay, if I draw a graph, for example, value of physical quantity, that means the values that we have got after our measurements, like just now we saw 2.32, 33. Okay, same. So on that x-axis we take the value. Okay, and here we take the number of occurrences. So we see a graph like somewhat like this. Okay, generally we see a graph somewhat like this. Okay, so we see that what do we mean really by this is, you can see a particular value, okay, or a particular value or a particular range of value. You can see here particular value or a particular range of value. You can see here occurs most number of times. What is it? Number of occurrences. That means how many times it has occurred. So a particular range of value, you can see here, it occurs most of the times. This is what we generally see. Okay, if you have not done any experiment so far in your life, okay, when you will do, you will see the same thing. Okay, we see that a particular range of values always occurs most number of times. Okay, so there is a range, you can see here. Okay, so this is really what happens. Okay, so that's why, and that is the reason why, considering the arithmetic mean as the best possible value and as the true value is the best thing to do. Okay, this is the reason. See, this is what we have seen in most experiments. Okay, almost every experiment gives us the same kind of a distribution of data. Almost every experiment gives us the same distribution. Okay, So that is the reason why we take the mean. Okay, that is the reason why we take the mean over here. Okay, so anyways, here also if you take the mean of all these values, you will get here only, and this is the value that has occurred most of the times. Okay, so definitely the value that has occurred most of the times must be at least near to the true value. Okay, I'm not saying it is true value, but the value that occurs most of the times, definitely, why not to consider this as a true value, isn't it? Okay, because it has shown its existence most of the times. Okay, it has occurred most of the times. Okay, so definitely, there is more chance of this value being the true value, and that is the reason why we take average or mean, and we consider this arithmetic mean as the best possible value, and this best possible value is then considered as the true value. Okay, so this is generally what we do. Okay, so I hope this concept of best possible value is very clear to all of you. Okay, now we move to a very important topic. Now we actually move over here. Okay, after all this, okay, so see, my job was to clear all the basics, okay, before I move on to this actual topic, because if I directly move over here, maybe it will not be directly clear or directly click, okay, in your mind. Okay, so I hope everything so far has been clicked in your mind. Okay, so now we will move to this absolute error. What is this absolute error? See, as an researcher, as an experimentalist, these terms are pretty much important as any experimentalist, because every experimentalist deals with all these things on a daily basis. Not on a daily basis, but many times. So that's why from their point of view it is very important, because they deal with the data. We generally don't, as a student, okay, as a teachers we don't, but researchers do encounter all this. Okay, so now let's see what is absolute error. See, we have just found out the mean value, right? We have just found out the mean value. We call it a mean. Now, how did we found out the a mean? By just adding all the readings, right? Adding all the values of the measurements, dividing it by the number of measurements. Okay, so let's say a1, a2, a3, okay, and up to an. These are up to an are the values. Okay, these are the values of the physical quantity that we have obtained in a particular experiment. Okay, and let's say a mean is the mean of all these values. Okay, so this is the mean, and definitely a mean is nothing but the true value. Okay, nothing but the true value, okay, of this physical quantity under measurement. Okay, when I'm saying physical quantity, it may be any physical quantity. Okay, right now also you can take any example that you want. Let's say it's a time itself. Let's say it's a time. Okay, so for while we were measuring the time, let's say a1 is the first reading, a2 is the second, this is third, and so on. This is the nth reading of the time, and we don't know which is the exactly the true value. What we do is we take the average or the mean, and that we consider as a true value. Okay, okay, now we move to a very important topic, that is absolute error. Okay, so what is this absolute error? Okay, now we will see the definition of the absolute error. Okay, absolute error, very important, just check it out very carefully. Okay, so over here, okay, first of all, one thing I would like to clear here. See, absolute error is calculated for individual readings. Okay, absolute error is calculated for each and every reading. Okay, it's not the error, it's not something that we calculate with regards to the true value. Okay, it's something that we calculate for every measurement, every value. Okay, okay, so now what is this absolute error? Okay, so let's define it. So the magnitude of the difference, okay, the magnitude of the difference between the true value, okay, between the true value of the physical quantity and the individual measurement, okay, and the individual measurement. See here, the magnitude of the difference, okay, the magnitude of the difference between the true value of the physical quantity and what, the individual measurement is called as the absolute error of that measurement, okay, of that measurement. Okay, so see here what I am saying, the magnitude of the difference between the true value of the physical quantity and the individual measurement is called as the absolute error of the measurement. Okay, so what do we really mean by this? Okay, I will show you. First of all, this absolute error is denoted by delta A. Okay, and see, you can see these lines. These lines means it's a magnitude only. Magnitude means there is no sign. Okay, whether it is positive, negative, it is always considered to be a positive only. Okay, even if it is negative, we will take it as a positive. That's the meaning of magnitude. Okay, so over here, see how do we calculate? Suppose for A1, the absolute error, okay, would be delta A1, okay, delta A1 is equal to, see over here what we do, it's A mean, okay, minus A1, okay, A mean minus A1. Just now in the definition I said the magnitude of the difference between the true value, okay, true value of the physical quantity and the individual measurement is called as the absolute error of the measurement. Okay, so you can see here. Now if you go for the A2, then for A2 the absolute error would be delta A2 equal to A mean minus A2. Okay, now if you go for this third one, A3, okay, then for A3 this becomes delta A3 is equal to A mean minus A3. Okay, and if you go further, let's say for the nth reading, so for AN, okay, it is going to be how much? Delta AN equal to, again, A mean minus A nth. Okay, so this is the formula for the absolute error. Again, I am telling you, absolute error is calculated for each and every reading or every measurement. Okay, so by doing this, what we are doing here is, see, by finding out this absolute error, what we are actually doing, we are actually finding out, okay, we are actually finding out how far or how close the individual measurement is to the true value. Okay, how far or how close the individual measurement is to the true value. Okay, because this number will definitely show us, isn't it? It will show us how close it is to the true value or how far it is from the true value. For example, let's say for example, some values like A1 is equal to 1.31, A2 is equal to 1.29, A3 is equal to 1.30, okay, 1.30, A4 is equal to 1.32, A5 is equal to 1.30, let's say 30, okay, and let's say nth value is, okay, 1.31, for example. Okay, so you can see all these are very close to each other. Okay, now if you take the average of this, you will get the mean. Okay, you will get the mean value, that is nothing but the true value. So let's say for example, I am not calculating, but let's say for example 1.30, okay, let's say 1.30 is the average of all these values. I really don't know what is the average right now, but let's assume it is 1.30, okay, at this moment. Okay, so now using this number we can actually find out what is the absolute error in A1. How you will find out? Just this A mean minus A1, isn't it? A mean minus A1. So in this case, what would be the absolute error? Delta A1, you can see here. A mean is what? 1.30. This is 1.31. So it is going to be 0.01, isn't it? That would be the absolute error. Same here we can do. Delta A2. How we can do this? See here. This is 1.30. This is 1.29. So it is again 0.01. We can do the same thing. Delta A3 is equal to again 1.30, 1.30. Okay, it is how much? 0.00. Now we go ahead. 32. So here it would be delta A4. Okay, this would be 1.30 minus this. So it would be how much? 0.02. Okay, see here, if you do this 1.30 minus 1.32 or this also, you are gonna get a negative number. But we have chosen what? We have chosen magnitude only, not the sign, for some reasons that will be clear very soon. Okay, so in this way we can go ahead and calculate for this one also. Delta A5, again it would be 0, right? 0.00. Again if you go here, delta AN, it would be equal to 0.01. Okay, 0.01. Okay, so we can find out these absolute errors in each measurement like this. It's very simple, isn't it? It's very simple, nothing much over there. Okay, so each of these values, you can see here, each of these values are actually telling us, okay, how close, how far these values are from the true value. Okay, we are so actually by finding the absolute error, we are just trying to find out a difference between the true value and the individual measurements. Okay, I mean how close we are, how close our measurements are, how far our measurements are from the true value, where we are lacking, what is the problem, where is the problem. Okay, where is the problem? So we are actually trying to find out these things over here. Okay, so this is nothing but the absolute error. Okay, so I hope this is clear how to find out the absolute error in any reading, any measurement. Okay, it's very simple. It's a magnitude, remember. It's not a negative number anytime. It's just a magnitude. Okay, so now we move ahead. Now we see another very important term called as the mean absolute error. Okay, next is the mean absolute error. Now this one is again denoted by delta A mean. Now what is this mean absolute error? So from the name itself we can suggest it's a mean of absolute errors. So over here we have found out the absolute errors, okay, in each of these readings. Okay, each of these readings. Now we will do the average of all these absolute errors, individual absolute errors, and that would be nothing but the delta A mean or mean absolute error. So that's very simple. Delta A mean is equal to what? Just these numbers added. Okay, delta A1 plus delta A2 plus, okay, there are n number of terms delta A nth. Okay, and all this divided by the number of terms, that is n. Okay, so this gives us the mean absolute error. Okay, so first we found out the absolute error. That means what is the error or uncertainty in each value. Now we found out what? The mean uncertainty, okay, or the mean absolute error. Because what are these absolute errors telling us? Nothing but the uncertainty, isn't it, in each of the values. Same here. Now what we have found out is mean absolute error. Okay, so that means we have actually found out the mean uncertainty in our mean value. Okay, these absolute errors are talking about uncertainty in individual measurements. Now this value over here talks about the uncertainty in the true value or the mean value of all these numbers. Okay, all these a1, a2, a3 up to an. Okay, so this is what we call as the mean absolute error. Okay, just the average of each absolute error, average of all these absolute errors. Okay, so now after all this, we come to a very important representation. Okay, very important representation. See over here, we have now found out what is the true value. So that a mean is called as the true value, as we all know. Okay, a mean is called as the true value. Okay, now, so now we know what is the true value, but at the same time we also know the mean absolute error, isn't it? Mean absolute error, mean. Okay, mean, it's an average. Okay, it's the average. Over here, before we found out the absolute error, that means what is the error in individual values. Now we have found out the mean or average error. Okay, what is the average error in a whole experiment? Okay, that is what we have found out over here. Okay, so delta A mean is nothing but the mean uncertainty or average uncertainty in our experiment. Okay, so whenever we found out all these things, okay, whenever we found out all these things, so what we do is the physical quantity that is under measurement, let's say we are measuring a physical quantity A, as now we have seen. Okay, A, so this A, the final result, okay, the final result would always be represented as A mean, okay, plus or minus delta A mean. Okay, A mean, okay, plus or minus delta A mean. For example, I will show you. Suppose these are this A1, A2, A3. They are nothing but some readings for time. Let's say T1, T2, T3, T4, okay, T5, and up to Tn. Okay, so these are time. Okay, so that means we are finding out the value for time. Okay, let's say. So what we have got is this as the best possible value. So what we will do is we will write here 1.30. Write down 1.30. But we see here that there is a little bit of a uncertainty, isn't it? So what we do is we find out the mean of all these uncertainties and we write over here plus or minus whatever is the mean of all these numbers. So we have to calculate that. So for example, let's say it is 0.01, just example. Okay, so any physical quantity is always represented like this. Okay, first the best possible value, okay, plus or minus the mean absolute error or the mean uncertainty in it. Okay, this is how we generally represent any physical quantity. Okay, so first we find out the mean value of all the measurements, then we find out the absolute errors in each of the measurement, then we find out the mean absolute error, and then we represent any physical quantity like this. A is equal to A mean plus or minus delta A mean. Okay, that is what we do. Okay, so now what do we really mean by this? Okay, what do we really mean by this? See, over here we have written plus or minus, okay, A mean plus or minus delta A mean. Now definitely this number is pretty small. You can see here, this number is generally very small in comparison to the mean value. So there is no question with that. But what does this mean is, from the point of view of any scientist or any researcher, any experimentalist, this actually means that we know the true value. The true value is 1.30, but I think there is an uncertainty. Maybe it is 0.01. Okay, this is what we mean by this kind of a representation. Yes, I know the true value, it is 1.30, but I think there is a uncertainty in it, that is 0.01. Okay, that's why we have written it like this. Okay, but I don't know whether it is more or less. It may be 0.01 more or 0.01 less. Okay, I don't know, who knows. Okay, so what do we really mean by this is t can have two values. T may lie, may, okay, we don't know the actual value, but t may lie in the range from 1.30 minus 0.01 to t equal to 1.30 plus 0.01. So if you do this, t is equal to 1.29, okay, and to here t is equal to 1.31. So the mean value is 1.30, that is, this is our best possible value, but it has an uncertainty. Okay, we say no, maybe the time period, okay, is not exactly 1.30. It may lie in the range from 1.29 to 1.31. We don't know the exact value, but maybe it lies in this range. This is what we mean when we represent any physical quantity in this way. Okay, so in a general way we can say this A, okay, lies in the range A equal to A mean minus delta A mean to A equal to A mean plus delta A mean. So that is our uncertainty, because what is error? Uncertainty. So this is what we are doing. This is the way we are representing the uncertainty. Okay, so A lies in the range from this to this. Okay, so this is the way to write down, okay, any number. Okay, any measured quantity is written always like this. Okay, scientifically. Yes, in your books now, if you check, generally you will not find out the quantities written in this way, because people don't show us those uncertainties in our books, at least. Okay, most of the times we ignore this. Okay, because it is very less in comparison to the true value that we take. Okay, so, but yeah, scientifically we have to consider this. Okay, when we actually deal with problems, we consider the uncertainty also. Okay, we keep it in our mind, we keep it under consideration. Okay, so this is absolute error, this is mean absolute error. Now we move to the another one, that is the relative error and the percentage error. Okay, very important again. Okay, relative and percentage error. So let's see. So first of all, I will talk about the relative error. Relative error is nothing but the ratio. Okay, it's a ratio. So I will write here, relative error is the ratio of delta A mean. What is the delta A mean? Nothing but this mean absolute error to the mean value. Okay, to the mean value of the physical quantity. Okay, so this is the relative error. Okay, this is the relative error. What? The ratio between mean absolute error and the mean value of the physical quantity, or you can say the true value of the physical quantity. Okay, so it's just the ratio of mean absolute error to the true value of the physical quantity. That's it. That is the relative error. Okay, this is the relative error. So you can see here, in a way we are checking what is the value, what is the error relative to the true value. Okay, what is the error? Okay, what percentage of error is there in comparison to this? Okay, in comparison to mean value. Okay, now if you go to the percentage error, it is similar to this. Okay, percentage error, over here we can write the percentage error, okay, is equal to see, defining this is very simple. It's nothing, it's related to this only. Whenever relative error is written in percentage, okay, whenever relative error is represented in percentage, okay, percent, you know percent, right? I hope you know percent. Okay, so whenever relative error is represented in percent, then it is called as the percentage error. That's it. Okay, so here it is, relative error and when you multiply this by 100, what you will get is a percentage, isn't it? Okay, this is nothing but the percentage. This is how you find out the percentage, right? Okay, for example, how do you calculate the percentage of your marks? Okay, suppose the total marks are 500 and you got, let's say, 350. So how do you find out this percentage? The marks obtained divided by the total marks, okay, into 100, right? Same here we have done. Okay, see, this is the error, okay, divided by the mean value into 100. Okay, when you multiply by 100, it gives us in percentage. Okay, so here we can see it's going to be 70% marks. Same here we can do. Okay, we just first have to find out the relative error. First find out the relative error, multiply by 100, you will get the percentage error. Okay, that's it. This is how we do it. Okay, so this is the percentage error. Okay, and this is the relative error. Okay, so I hope this is very clear. Okay, so in this way, in this big lecture, we have seen what are the absolute error, okay, and the mean absolute error, then the relative error, and then the percentage error. Okay, see, I could have just defined them, okay, in a 5 minutes, but that would have not been fun. That would have not been so clear. Okay, for the people who don't have any background, okay, for them this was my job to, you know, elaborate as much as possible, okay, give as much information as possible. That was my job. So that's why this was a little bigger lecture in comparison to the topics that we have covered. Okay, so we have just covered absolute error, mean absolute error 2, then relative error, then percentage 4, and yeah, one more, that is the best possible value or the true value. So 5 topics. Yeah, so it's it's okay, I think, for 5 topics and nearly 1 hour lecture. It's okay. Okay, so in this way we have covered so much in this lecture. I hope everything is clear. Okay, if you have any doubts regarding all of this, you can ask me in the comment section. Okay, but again, I hope there would be no comments regarding doubts, because I feel everything is clear. But still, if you have any doubts, you can definitely ask. I will definitely answer you. Okay, so now we will stop over here. Okay, I will see you in the next lectures. Okay, in the next lecture we are again gonna see some more interesting fun topics regarding errors. Okay, and again we'll meet. Okay, so thank you so much for joining over here. Thank you so much for listening. Thank you so much for watching. Okay, have a nice day. Bye bye. See you.